11:05. Welcome all. I think we can start with this Trumpet exchange talks. So first of all, I would like to thank you for being here today with us, and for sure also thank you to all the speakers, like Xavier, Luaña, and Héctor from Gradiant. Gradiant is a leading company based in Spain, and basically they are involved in all the innovation processes in the ICT sector. And their product, their services are related to different goods that really are related to not only just healthcare, but in different topics. Today we are together because of we are collaborating in a Trumpet initiatives, which is a EU-funded project, and basically our idea was to spread knowledge and to increase awareness about these topics among all the technical professionals and all the people interested in that. So we will stay together in the next 45 minutes. So again, thank you all of you for being here, and I directly leave the word and the screen to, I guess, Xavier for starting the presentation. Just remember, this is recorded due to reporting purposes.
Will you share the presentation, Gonzalo?
Yes, just 1 second. Sorry. Can you see the screen?
Yes, thank you.
Okay. So my name is Gonzalo. I'm going to be one of the speakers of this webinar, along with Héctor and Xavier. So the contents of this webinar will be the following. We will start with an introduction to the Federated Learning platform we are developing in Trumpet project. They are going to introduce the different privacy enhancing technologies that we are using to protect some parts of this Federated Learning process. And they are going to give some information of how we are implementing this Federated Learning platform, and then we will conclude with conclusions and some benchmark of the implementation we have done until now. So I give the floor to Héctor to introduce you this Federated Learning platform we are developing.
Okay, can you hear me?
Yes.
Okay. So the proposed design for the orchestration of a federated learning process is based on federated sessions, as we can see here in this state chart. So in other words, to carry out a federated process, a multi-party session must be established where all the data owners agree to participate in the federated process. This session expires once the federated expires at the end of the federated process once the federated learning training was done. So in this state chart, we can appreciate these behaviors. If you notice here, there is an entry point to the state chart when we can read state federated learning process, and we have some states which requires authorization from all the domain owners. So the establishment of sessions in a cross-silo federated learning scenario is a fundamental part. So in this type of cross-silo setting, it's very common to have a low number of participants, but each participant have a large amount of data. So the risk that any participants may have is usually much more higher than any other scenarios, like, for example, cross-device. Therefore, the initiation of a training process requires individual authorizations from each domain owners. With this federated session requests, information from other domain owners is shared, as well as different metadata from the federated training. And based on this information, the domain owners can deny or accept to use their local private data on the federated process. You can pass this slide. Okay, so in this figure, we can see the different federated learning phase we have defined. The phase 0 and 1 corresponds to the previous slide at the state chart. When we talk about the establishment of federated sessions and the approval of private data for the federated learning process. More specifically, the phase 0 corresponds to the publishment of the information of the participants, and the phase 1 is when the researcher shares information about the machine learning model and how private data will be used. The phase 2 corresponds to the local training of the domain owners using their private local datasets, and this process generates a local model. Then in the phase 3, the domain owners upload their local model parameters to the aggregator. And in the phase 4, the aggregator aggregates all the uploaded model updates from all the domain owners. And then the aggregator sends back the aggregated model to all the domain owners. And this process is repeated until the model reaches some kind of success state, for example, the convergence, or for a fixed round federated process. Okay, you can pass to the next. Okay, so although we all know that federated learning was also proposed as the ultimate safeguarding of data privacy, it might not be like this, because further research raised important questions about the protection offered by that approach. So different vulnerabilities such as aggregation attacks, man in the middle, and insider attacks were pointed out. So, for example, one of the most prominent attacks are aggregation attacks. The aggregation attacks allows an adversary to infer sensitive information from the aggregations of the data. And man in the middle or insider attacks allows to disrupt or maybe modify the model convergence inside a federated process. And the inference attacks is one of the most dangerous because it allows an attacker to re-identify the local private data of the data owners. And these vulnerabilities expose important security and privacy considerations that need to be rigorously addressed to ensure trust and effectiveness of federated learning in practice. To meet this challenge related to the security of federated learning, we can distinguish three main categories. The first one is the statistical privacy, which aim to disrupt the output of the federated process, obtaining an approximate result and hiding sensitive information at the same time. For example, one example of this strategy is differential privacy. Then we have verification strategies, These strategies aim to verify that all parties perform their work correctly without revealing more information than the result. These strategies are commonly known as zero knowledge proofs, and sometimes with the help of homomorphic encryption or maybe encrypted computing. And lastly, we have encrypted computing strategies. These strategies aims at calculate a result without sharing any of the inputs of the part. These techniques include, for example, secret sharing, homomorphic encryption, and code-distributed computing. Next, please. So, in the context of federated learning for secure aggregations, we have two main objectives. Protect the local model updates from the domain owners, and protect the aggregated model update, which is the final global model. So from this point, we can define input privacy, which is a guarantee that one or more people can participate in a computation in such a way that neither any party learns anything about the other party's input. And output privacy, which is about ensuring that certain subsets of information do not make it through the information flow.
Thank you, Héctor. Now I will continue with to explaining one of the privacy enhanced technologies we are using to protect the federated learning process. In this scenario we're building, what we're protecting right now is only the aggregation process. And for example, one of the techniques that we can use is homomorphic encryption. Homomorphic encryption is a cryptographic technique that allows to compute over data that is encrypted. So the I don't know if there is a question right now, or should we wait to the end?
No, I don't see any kind of questions.
I saw someone
just
raise their hand.
Wait.
I saw
you saw an end, right? So I think we can just take the question after the talk. So please, if you want, also you can use the chat and also write in your question. But in the final part, there is a possibility to unmute and to ask the question to speakers. Thank you.
Okay, so as I was saying, homomorphic encryption allows to perform computations over data that is encrypted, so the entity that is performing this computation has not access to the clear test data that is being computed on. There exist several different types of these schemes. The first one that were introduced were the partial homomorphic encryption schemes that allowed only to perform one operation that could be the addition or the multiplication, but not both at the same times. Later, somewhat homomorphic encryption schemes appear. These schemes allow to perform both additions and multiplications over encrypted data, but have some bounded limit of the number of operations you can perform over encrypted data without having errors in the decryption. So later on, fully homomorphic encryption schemes appear that allowed an unbounded and unlimited number of operations that can be applied over encrypted data, thanks to an operation called bootstrapping that allows to reduce the noise of a ciphertext encrypted some data, so it can be again operated through the homomorphic primitives of homomorphic addition on homomorphic multiplication. So these schemes can be used in federated learning, for example, to protect the aggregation process that is done the central aggregator. These scans in the classic setting use only a single key. They can be used in a federated learning setting. So in this case, all the data owners will have the same set of public and secret keys. So they will encrypt their local trained models with the same public key. These local trained models of each data owner will be sent to the aggregator that will be in charge of doing the encrypted aggregation, and then sending this encrypted aggregation back to the data owner so they can decrypt it and continue with the next round of the federated learning process. But this has a problem that if the aggregator colludes with one of the data owners, since they are using all the same key, the aggregator is able to decrypt the inputs of the remaining data owners, so the privacy problems persist in this type of schemes that use only one key. So to tackle this, new homomorphic encrypted schemes that use multiple keys appear in the literature. There are two main families that are ones are the threshold fully homomorphic encrypted schemes, and the other ones are the known as multi-key fully homomorphic encrypted schemes. And these type of schemes are most suitable for a multi-party scenario like federated learning. Using a homomorphic encrypted scheme with multiple keys, each data owner has his own set of keys, public and private. They encrypt their local trained models with their own keys. These encrypted models are sent to the aggregator, and the aggregator can perform the aggregation of the encrypted models that are encrypted with different keys using one of these schemes and send back the aggregated model to the data owners. But in this case, for the decryption, the data owners have to run a collaborative protocol that involves all of the private keys of them, so they can obtain the aggregated model in the clear, so they can continue to train further rounds of the federated learning process. With this type of schemes, the collusion between the aggregator and data owner doesn't allow them to reveal the inputs of other data owners, so the privacy of the input is protected. We have, as I introduced before, two main types of these homomorphic schemes with multiple keys. One of them is the threshold homomorphic encryption, and the other is the multi-key homomorphic encryption. Both of them have some advantages and disadvantages. In the case of threshold homomorphic encryption, one of the advantages is they have flexible access structure for distributed decryption. You can set a threshold of the number of data owners that you need to do the collaborative decryption. That can be the data owners less or equal to the total number of data owners that participate in the federated learning process. The homomorphic computation in this type of schemes have almost no change with compared to a single key homomorphic scheme, and has a reduced overhead compared to this type of schemes. But has some disadvantages that the setup phase for this type of schemes involves the execution of a collaborative protocol among the involved parties to generate a collective encryption public key that allows to encrypt the local trained models with this collective public encryption key. And also to revoke this key requires to run the protocol for generating the key and also re-encrypt all the data that was encrypted before. On the other hand, with the multi-key homomorphic encryption schemes, each user encrypts the data using his own secret key. So there is no collaborative protocol to generate a collective public key. So this is the setup phase is faster compared to threshold morphic encryption. But on the other hand, the disadvantages is that it presents a significant change and overhead compared with the single key homomorphic encryption. For example, to compute two homomorphic encrypted models, to aggregate them, that if they are encrypted under different keys, a primitive from multi-key morphic encrypted schemes that is called expansion to a primitive that is called expansion has to be computed that allows to transform a ciphertext that is encrypted with regard to the public key of one of the data owners to be extended to a public key that involves the public keys of the one data owner and the other data owners. So this process has to be repeated many times to take into account of the public keys that are involved in the process of aggregation. Also, if the group of parties that participate in this federated learning process remains unchanged, there is an overhead in the extension of the ciphertext that is proportional to the number of parties participated in the federated learning process. For these reasons, we have chosen to use a threshold homomorphic encryption because in this federated learning process, the data owners are the same in the several rounds that are run in a federated learning study. And also the setup phase, we only execute them at the beginning of the federated learning study. So in the different rounds of the protocol, of the local training that are run of the iterative aggregated models, we don't have to recalculate this collective public key. So it's more efficient than the multi-key or homomorphic encryption schemes. These threshold morphic encryption schemes has a series of primitives. Some are similar to the classic single key homomorphic encryption schemes. The first one is the setup that given a security parameter lambda, it generates a public parameters for the scheme that are the input for the primitive for the key generation. Each of the data owners generates their own public and secret key pair that are then used. These public keys are used to generate a collective public key and also the evaluation keys, keys for the homomorphic encrypted schemes. There is also an encryption primitive that uses the collective public key for encrypting a message into a ciphertext. There is also an evaluation primitive that takes as input the public and evaluation keys, a function, the ciphertext that are going to be computed by this function, and outputs the result of this function in the encrypted domain. Then for the decryption, we have two different approaches. One will be to directly each party use its secret key to do a partial decryption, producing a partial decryption of this data owner, and then they have to run a multi-party protocol that combines its partial decryption to obtain the final the result of the aggregated model. Or it's also possible to run a collective key switching protocol that takes the secret key of each data owner and the result ciphertext to generate some outputs that we call here H, and then they run a collective protocol to generate from the original ciphertext, that is the encrypted aggregation of the local models, to generate a new ciphertext that encrypts the same aggregated model, but with regard to the other a different secret key that they all know, so they can do a local decryption with that secret key. For implementing this threshold homomorphic encryption scheme, we leverage the Go module called Latigo, developed by the Tunisian company, that provides a series of multi-party homomorphic encryption primitives. It also supports the use of several homomorphic encryption schemes like BFV, BGV, and also CKKS. The two first one work in the integer domain, but the CKKS works with approximate rational numbers, so allows to directly work with floats and takes does the conversion from floats to the encrypted domain. But in the case of the first two ones, we have to do a processing to transform real numbers to integer numbers before they can be encrypted and operated on. In our case, we have chosen to use the BFV scheme provided by the Latigo library. One thing that the Latigo library doesn't provide is all the communication primitives that are needed to be run among the different data owners to run the collaborative protocols. So for this purpose, we have implemented a Python wrapper of the Latigo library that allows us to access basic primitives. And then in our implemented platform, the platform that is implemented in Python language, we implement this communication protocol that allows to exchange all the information needed to run these collaborative protocols. The primitives that are provided by Latigo are the collaborative public encryption key generation, and also the collaborative public eval key generation, with the different type of keys that are using for the evaluation of functions in the encrypted domain. And it also implements the function for do the collective key switching that allows to change for a ciphertext that is encrypted with regard a secret key that all the parties share, but they don't know as a whole. They use a linear secret sharing scheme that where they each of them owns a share of this secret key, and they can run this protocol to change from this collective key to one they know beforehand, so they can then do the local decryption of the aggregated model. Since we are using a threshold homomorphic encryption scheme that allows to select P out of M parties to be able to do the decryption, we have chosen to choose a scheme that uses N out of N setting. So all the involved parties in the federated learning process are needed for the decryption of the aggregated model. For this, we use a linear secret sharing scheme for the generator collective public key, which each of the local secret keys of each party is used in a collective protocol to generate this collective public key. Since participants have large amounts of data in their own databases, their information is important to train a global model. So they all participate in each round of the federated learning process to train this global model. So it's important that all participate. For the reason we all of them participate in all of the rounds. That is why we have chosen to use an N out of N setting. And this gives us some improved security because it allows up to all the data owners step one to collude. So even in that case, they are not able to decrypt the inputs of the remaining one. So the privacy of the input is maintained in this sense. So going back to our federated learning platform, by introducing the multi-key or multi-party homomorphic encrypted schemes, we add some phases, some steps to the federated learning process. One is the setup that allows us to configure the homomorphic encryption parameters. Then we run the key generation that is only running in the first phase. Then after the local training, each data owner encrypts the local models. Each local model from each data owner is sent to the aggregator. The aggregator aggregates the encrypted models and then send the aggregated encrypted model to all of the data owners, and they have to run a collective protocol that allows them to obtain the aggregated model in the clear, so they can run the next local training round and repeat the process until the model, the global aggregated model converges. So now I give the floor to Xavier to talk of other privacy enhancing technology we are using in our federated learning platform.
Okay, thank you, Gonzalo. Yes, I will talk about coded distributed computing. This is a computing paradigm that uses coding theory to mitigate maybe not all, but most of the fundamental bottlenecks of large-scale distributed computing systems. Usually, these are related with communication overhead. Portion of time you spend exchanging information instead of actually computing functions, which is the main objective of the systems. Presence of stragglers notes that for various reasons have less efficiency than the others, and this might affect the overall efficiency of the system, and also security of data. This mainly refers to input or output privacy, but might as well be referring to input or output verification. The specific types of security that will be provided by these systems will, of course, depend on the scheme that we select. As this coded distributed computing paradigm is based on large-scale distributed computing systems, of course, federated learning can be placed in there, as it's just one specific use case of a distributed system. So next slide, please. So I have just noted here some interesting works that can be leveraged in this field. There are many more, but if we separate them by the type of operations that they are focused on, we have polynomial operations. We have famous Lagrange coded computing, which is like this unified solution for any multivariate polynomial operation that aims to be optimal in the three bottlenecks that I explained before. We have an analog version of this Lagrange coded computing that acts on the analog domain for computation of real numbers. Then we have also entangled polynomial codes, which are focused on the partition of data, not only about security of computations, but also being able to do complex partitions of input data, not just regular ones. And then the last three that you can see there are focused on matrix multiplications. We have secure coded multi-party computation that uses polynomial codes for massive matrix multiplication, coded sketch for approximating matrix multiplications in presence of stragglers, and this last one, fully private and secure coded matrix multiplication that uses one type of encoding technique called convolutional coding to also privately and securely compute matrix in presence of stragglers. Then different type of operations more specific to machine learning. We have harmonic coding, which leverages harmonic progression to efficiently compute any type of gradient function. And finally, there's this per-root approximated coded computing, which is a technique that tries to solve some of the problems that Lagrange coded computing has, mainly numerical stability issues, but and allows to compute complex operations, not only polynomial based operations, any sort of operation. The main downside that it has is that it does not natively provide privacy, so we could not use it as it is. If we wanted to use it, we had to or combine it with another technique, or maybe use or maybe modify it. So next slide. So what we did was focused in Lagrange coded computing. As I said, this a universal technique for multivariant polynomial computations that have the main objective of computing a function over a given dataset. It will have k partitions. This dataset will be owned by a master, and the computation will be done using n workers. As this computation happens, the input dataset will remain private, and the reconstruction of the result can be achieved in presence of straggler nodes, in presence of colluding nodes, and in presence of adversarial nodes. Colluding nodes and stragglers are already mentioned, but adversarial nodes, we understand them as any entity that wants to maybe do some small modification on the information that it exchanged to gain a benefit. For example, to obtain more information than the one they're obtaining just by following the protocol. As you might have noticed, it's based on Shamir secret sharing as the main block of operation, and it has the following steps. We first have an encoding and sharing step where the master encodes the private dataset using the Lagrange interpolation polynomial as the encoding function, and t random elements that will specify the threshold of colluding nodes that the system will resist. The system does not specify the set of points that should be used for constructing the polynomial or for evaluating it. As from a theoretical perspective, multiple could be used, but in practical, and it will be discussed later, in practical, some distribution of points are better than others to avoid numerical instabilities. And once this dataset is encoded, they evaluate the polynomial in different points, and one of these points, each share, it's changed with each worker. And then we have the computation and communication phase, where each worker evaluates the function objective that can be anything as long as it is a polynomial operation over the encoded share received, and then retrieves the result back to the master. The master then applies Ritz-Solomon decoding to reconstruct the result in presence of errors, so that those errors will be the ones introduced by the adversarial nodes. This reconstruction is possible as long as this condition that I placed there this condition holds. It depends on the number of partitions that you do, the threshold of colluding nodes, the degree of the function, the number of stragglers, and the number of adversaries. You will have to adjust these parameters depending on the type of network that we work on. So next slide, please. So one of the limitations of LCC is that it relies on quantifying the data into finite fields, right, from Shamir secret sharing. And this is not scalable when the size of the input grows and the number of nodes in the network, mainly due to the computation overflows that might appear. So one possible approach is using analog Lagrange coded computing, which proposes to solve this limitation by carefully selecting the distribution of points that will be used in evaluation and in the construction of the polynomial. So the interpolation points where the data and the randomness will be encoded are what you can see in this figure, the betas. It's a representation of the points in the complex domain, and they are the roots of this beta number, which is a real number greater than 1. And then we have the evaluation points, the ones that will be assigned to each node, which are the roots of the unity. And with this distribution, we can overcome the problem of Lagrange coded computing and operate with real numbers, with floating point, which is the main objective and it's very common in machine learning. So next slide. But now, as explained until now, it's more like a MapReduce setting, more like a federated learning setting. So we have to adapt in some way the scheme to be used by multiple data owners. We don't have workers now, and we don't have a master, we have an aggregator, and we have nodes that own data and share it with each other to compute the function. So we adapted the phases by the encoding and sharing phase. Now it's done by each data owner, encodes its private model parameters using the already mentioned Lagrange interpolation polynomial, and shares evaluation with each other. Then computation is done over all of the received shares, not just one received by the master, but all of the shares received by the other parties. And the result that it obtains, it's sent to the aggregator. The aggregator will decode, applying some decoding technique, and reconstruct the result if the condition holds. After the aggregated model is reconstructed, it will be returned to the data owners. As one of the things that in gross-silo federated learning does not usually have stragglers, so this means that this leaves room to improve in another aspects of the protocol. If we don't have stragglers, we can improve, for example, the threshold of colluding nodes that the system can resist, or we could maybe the threshold of adversaries. But this up until this point, this technique that I explained just provides input privacy. So we have to find a way of providing output privacy, so we can compare the scheme that Gonzalo explained and the one that I'm just explaining. And that's where differential privacy comes into play. Differential privacy is just a technique that involves adding control noise in a way that ensures that the presence or the absence of an individual data record in a dataset does not have an impact on the outcome of an algorithm. So in federated learning, usually the noise is introduced in the model parameters, and the amount of noise that you add will depend on a value, an attribute called the privacy budget. I will not enter in detail in this, but just as a brief description, we have implemented a combination of a sparse vector technique and selective parameter update. Sparse vector technique just consists on sending some selected weights with noise, so we can guarantee privacy without consuming the privacy budget in each iteration. And a selective parameter update is designed to reduce the impact on large weights on the overall computation. So we only share weights that are greater than a threshold, and these weights are clipped to a pre-established value. So now that we have all of the pieces, we can see how this fits together in federated learning. There are the main steps that Héctor already explained until the local training. It ends up with every data owner having a local model parameters that have to be protected in some way. So we first do the noise addition phase, which is the differential privacy protocol that I just explained. Then we do the encoding part of LCC. This encoding then implies a sharing of the shares with all of the data owners. And then when all of the data owners have these shared versions, shared encoded versions of the parameters, they will evaluate the aggregation function. Once this partial aggregation is computed, they will share it back to the aggregator, and the aggregator will, with all of them or some of them, will do the decoding of the aggregated model, but in this case will be a noisy aggregated model, so we will have output privacy as well. And then the noisy aggregated model goes back to the data owner, and the process continues until we achieve convergence. And that's it from my part. Thank you.
Okay, so thank you, Xavier. I'm going to talk about the federated learning platform and how we integrate these techniques. So here we have a slide presenting the main characteristics of our federated learning platform. As I said before, it's a cross-silo setting. So the federated learning concept is expand to encompass collaboration and model training across multiple domains. So this approach allows different entities with private data to collaborate and build efficient machine learning models. So our platform is also designed to address the issue of data governance and privacy. One of our main objectives is to maintain the decision-making authority of over the data of authority over the use of private data in the hands of the domain owners themselves. Through this, the domain owners can preview information about what data is going to be used in the federated process, the machine learning model that is going to be trained, how that data is going to be used inside that training, and based on that, domain owners can accept or reject the participation on the study. And one of the main reasons for building a federated learning platform was communication optimization. Federated learning processes can be quite cost in terms of computation and communication, and if we add privacy enhancing techniques to that process, it's even worse. So we needed a very optimized communication module, so privacy enhancing techniques were feasible. Next slide, please. Okay, so here we have the an overview of the platform's architecture. In this figure, we can appreciate two main schemas. The first one is based on PyShift. We use PyShift in our platform to communicate the domain owners for the phases 0 and 1. Thanks to this library, we can upload the private data to the platform, exchange information about the machine learning model, some code executing policies, data usage, and etc. So in this PyShift scheme, we can also distinguish PyShift domain nodes and gateway nodes. Gateway nodes are used for interconnect these domains and share information between them. And PyShift nodes are the main block of federated the phases 1 and 0 functionality. And in the other side, we have our custom communication platform. So since we found that there was some limitations by the PET adoptions into our platform, we thought that developing our own communication model is going to be more efficient. So this communication model is used for the phases 2, 3, and 4. In general, for orchestrating the whole federated process and insert privacy enhancing technologies when it's needed. And this custom communication module can employ the PET module, which contains the encryption-based PETs, which Xavier and Gonzalo presented you before. And each domain owner and the aggregator have a custom node which interacts with all of these components in order to orchestrate the whole federated learning process from the phase 0 to the phase 4. Next slide, please. Okay, so in order to perform the correct integration of PETs in the platform, we decided to conduct a a federated learning process for validation and then compare the results. For this validation process, we select the breast cancer Wisconsin dataset, which was divided into train and test set, 50% train and 50% validation. Since it's a distributed training, we select each domain owner and partition the datasets. As we selected 3 domain owners, we selected we split the dataset, the training dataset, in 3 portions, and each one was sent to each domain owner. So for the training model to be trained, we selected a logistic regression model, which can predict the likelihood of a breast cancer presence, and then we selected a simple federated averaging algorithm. Next, please. So in this figure, we evaluate how the model performs by the F1 score on the test data. The test data is data that has not been shown in none of the local trainings. Here we show the evolution of the F1 score through the federated learning rounds. So we can appreciate how the model improves its prediction capacity on each round. This figure also shows great results, since we found that both PET combinations do not compromise the quality of the final model, the final aggregated model, which is a fundamental requirement for this project. We also show a table where we compare communication and computation times for each privacy-enhancing technology. And also multi-key homomorphic encryption shows superior efficiency in the aggregation function, and LCC SVT excels in input and output privacy. The overall convergence times for the models remains comparable, so this makes both approach feasible in cross-silo federated learning environments. Okay, and that's it. Yeah, I don't know if anyone has any questions.
So thank you, guys, for these insightful talks. So basically, yeah, this is just time for questions, for comments. So please, or the members of the audience, if you want just to unmute and to ask questions, or if you want to write in the chat, we have just like 2, 3, 4 minutes for taking questions. Thank you. Probably you cannot unmute yourself, but if you raise your hand, I can unmute you. Maybe just I can start with the question related to the healthcare sector. So I'm not from the technical part, but anyway, you mentioned in the last part the involvement of the healthcare part, and for sure also related to the Trumpet initiative. Anyway, could you comment about which are the key points to take into consideration? Also, once we will move this technology to other sectors. So basically now we are focused on healthcare, but there is something very close to healthcare, which is pharma company and the way in which are produced and created drugs. So in your opinion, which kind of feature has to be maintained, fixed for this, for moving to another sector, this system? Sorry, can you repeat the last part? So which are the features that we have to take in consideration are always true if we want to move to the healthcare part, you just mentioned the last part of your talk, to another sector like pharma sector? in your opinion, in your comments. So because for sure, I probably could be like an investor. I could be like people interested in just exploiting this system to other part, other business. So which are the point that are always true that we have to take with us in this if we change the business.
Well, of course, it depends of the scenario. For example, we just simulated a cross-silo scenario. But if you move between cross-silo scenarios, the characteristics are pretty much the same. It might depend on some data regulations over the different countries, or maybe how each organization how strict is each organization about the data policy. But yes, for example, if we move to the pharmacologian domain, it can apply pretty much the same, but obviously it will depend depending of the organization, of course.
Great, thank you. Are there any other questions or comments? In the meantime, also remind you that this webinar will be uploaded to the YouTube channel of Trumpet Project. So please also, if you want to see again, or if you want to focus on a specific aspect of the talk, please go to subscribe to our channel, and in the next week will be uploaded there. Okay, so this is just the finish, the hands of the webinar. Thank you very much, Héctor, Gonzalo, and Xavier, for your insight on this great work we are working on. And again, so see you to the next Trumpet Exchange talks that will be in 2-3 months. Again, thank you all for being here today with us. Bye bye.